7.7 applications of the dot product and cross product. So formula for the calculation of work. Okay, work equals vector F dot vector S, where F is the force acting on an object, measured in newtons, N. S is the displacement of the object, measured in meters, and work is done measured in joules. Okay, so example 1. Mariana is pulling her daughter in a toboggan and exerting the force of 40 newtons, acting at an angle of 24 degrees to the ground. Okay, so let's draw the ground. Let's draw her pulling the toboggan, right? So she'd probably be pulling it like this. Okay, so the force is going to be 40 newtons, and it acts as 24 degrees. Okay, remember, this is the horizontal component, this is the actual resultant, and then this is the vertical component. Okay, so if Mariana pulls the child a distance of 100 meters, how much work is done? So when it asks us for work, it's W equals vector F dot vector S. Okay, what we want to do first is we want to get the horizontal component. So the magnitude of the horizontal component is going to be, okay, so if it's 24 degrees and we're looking at SOHCAHTOA, we're going to have cos 24 equals h over 40. Okay, so we have cos 24 equals magnitude of h over 40. We can cross multiply, so the magnitude of h is just 40 cos 24, which gives us 36.5 newtons. Okay, so this is 36.5 newtons. Now, calculate the actual work being done. Okay, so work is the force, which is 36.5, okay, times S, which is the displacement, which is in this case 100. So 3650 joules. Okay, so therefore she does 3650 joules of work. Okay, now the area of a parallelogram. So the cross product of two vectors, say vector A and vector B, okay, so remember vector A and vector B, they are tail to tail, okay, can be calculated, can be used to calculate the area of a parallelogram. So this is the equation, okay, the magnitude of A cross B equals the magnitude of A times the magnitude of B sine theta. Okay, so, and then a little bit of a proof here. So example 2, without calculating, explain why the cross products of J and K is vector I. That is, in other words, J cross K equals I. So we'll do this one first, and then we'll do one involving the area of the parallelogram. Okay? So if we think about it, J cross K is going to result in a vector. Okay, that is perpendicular to the plane determined by vector J and vector K. So it must lie along either the positive x-axis or the negative x-axis. Okay, using the cross product in the right-handed system, the vectors must lie along the positive x-axis. Okay, so if you were to go up here and you take a look here, okay, so we have vectors j and vectors k, okay, in order to be perpendicular, this vector must be vector I. Okay, and then if we were to think about the area of the square, okay, so remember vector I, j, and k are all unit vectors, so they're unit 1. So if we think about this is definitely going to be a square, not a rectangle. Okay, so let's name that square OKLJ, right? OKLJ. And the area of the square is going to be 1. Okay, so then therefore the length of the cross product is also going to be 1. Okay, so then in other words, it's going to be vector I. Okay, so coming back to the area of the parallelogram, determine the area of the parallelogram determined by the vectors, vector P and vector Q here. Okay, so we want to do the magnitude of P cross Q. So let's find P cross Q first. Okay, and we know that we're going to write out P twice, -156, -156. We're going to write out Q, 2, 3, -1, 2, 3, -1, and we're going to find the cross product. Okay, so ignore the front and the back, and we're going to go 5 times 1, which is -5, minus 3 times 6, which is 18. Now, 6 times 2, which is 12, minus -1 times -1 is 1. -1 times 3 is -3, minus 2 times 5 is 10. So we get the vector -23, 11, -13. So simply what we want to do is we want to now find the magnitude of vector P cross vector Q. Okay, so we're going to go -23 squared plus 11 squared plus -13 squared. And when we put that into our calculators, we get root 819, which is approximately 28.62 units squared. Okay, so that's going to be the area of the parallelogram. Okay, that's parallel. Okay, so a little bit more of a twist on this. Determine the area of the triangle formed by these 3 points. Okay, notice how these 3 are going to be points because they're capitalized. So if we actually think about triangle ABC, let's actually find direction vector AB. Okay, as a reminder, AB, we're going to go B minus A. So -1 minus -1. 0 minus 2, 0 minus 1. Okay, so vector AB is going to be 0, -2, -1. Now let's find one more direction vector. Let's find AC. Okay, so direction vector AC is going to go C minus A. So 3 minus -1, -1 minus 2, 4 minus 1. Okay, so we get 4, -3, 3. Okay, so here's the thing. We don't need this third triangle. Remember, the law for the parallelogram and the law for the triangle was just that it's going to be half of it. Okay, so we're going to just follow the same steps, and then when we get the area formed by, say it was a parallelogram formed by these two vectors, we're going to then just divide it by 2. So let's go AB cross AC. So let's write out AB twice. 0, -2, -1, 0, -2, -1. Let's write out AC twice. 4, -3, 3, 4, -3, 3. Okay, the front and the back we don't care about. Let's now multiply. So -2 times 3 is -6, minus -3 times -1 is just 3. Okay, -1 times 4 is -4, minus 3 times 0, which is 0. 0 times anything is just 0, minus -4 times -2, which is 8. Okay, so minus -8 is going to be positive 8. So we get the vector -9, -4, and 8. And now simply, if we want to find the magnitude of the cross product, we just do the square root of -9 squared plus -4 squared plus 8 squared. Okay, and we want 161, and that's going to be in units squared. Now, this is the area of the parallelogram, so we must divide by 2. So it's actually going to be root 161 over 2 units squared, or it's going to be 6.34 units squared, okay, which is the area of the triangle ABC. Okay, last application, torque. When dealing with forces that involve rotation or turning about a point or an axis, okay, so if we had a wrench and the wrench is this long, so we say radius because we're essentially, it would go in a circle, okay, when we're pushing it this way, our force is going here, okay. This could be tightening or loosening a wrench, turning a bicycle pedal to make the crank arm rotate, opening or closing a door, as all these examples have rotation about a point or an axis. Okay, the torque or turning effect of the force F, vector F, about a point M. Okay, so let's talk about this. Point M. Okay, this is going to be rotated on M, just like this wrench. And we're going to have some force, which is like the resultant, where we're going. This is defined by R cross F. Okay, the magnitude of the torque depends on 2 factors. It depends on exerted force, which is vector F, and it depends on the distance between the line of the exerted force and the point of rotation. Okay, in other words, like this radius. So magnitude of torque, so this is measuring the twisting effect of the applied force. This is D equals the magnitude of R. Okay, so R is going to be the direction vector for the radius, and then sine theta. And the magnitude for the torque, F about M. Okay, likewise, it's going to be the magnitude of vector R sine theta times the magnitude of vector F. And this is going to be R cross F. Okay, so example 4, and we're going to come back to this. A 20 Newton force is applied at the end of a wrench that's 40 centimeters in length. Okay, so already I'm thinking, okay, so we have some rotation from M. Okay, this is going to be 40 centimeters. And then some force is applied to that. Okay, let's call that 20 newtons. The force is applied at an angle of 60 degrees. Okay, so this is F. So let's go 60 degrees. Calculate the magnitude of the torque about the point of rotation M. So if we have the magnitude of R cross the magnitude of F, we are going to have magnitude of R sine theta times the magnitude of F. Okay, so first we're going to convert this 40 centimeters into meters. Okay, so 40 centimeters very easily divided by 100 is 0.4 meters. Okay, so we're going to use meters. So the radius is 0.4, and then we have sine theta. Okay, so when I'm thinking sine theta, I'm thinking, okay, let's go 30, 60, 90. Okay, and opposite 60 is root 3. Opposite 30 is 2 or 1. And then opposite 90 is 2. So when we have sine 60 in the next line, we're going to sub in sine 60 is root 3 over 2. Okay, now the magnitude of F. Okay, F is the force, that's 20 newtons. Okay, so the magnitude is 20. So when we multiply 0.4 times root 3 over 2 times 20, we get 6.93, and that's going to be measured in joules. Okay, so I just want to, so we can say the magnitude of the torque is 6.93 joules. Okay, the other thing I want to point out is when we apply force, okay, we apply force at right angles to maximize the force about that turning point. Okay, and I also want to say, i.e., the radius is going to be as large as possible. Okay, if you ever notice when you are turning something and it's very, very small, so say it's even 40 centimeters. If you're turning something that is, I don't know, 4 meters, it's going to be much easier to turn than it is when it's small. So you want to maximize the radius.